Hi everyone, welcome to our presentation. We are from Group 12. So Farid, Giri and myself, Mob, we are going to take you on a journey into a realm that challenge our deepest intuitions about logic and numbers, which topic is infinity beyond limits, countability and Hilbert's Grand Hotel. So, to explore the infinity, we first need to learn how to measure it. So, infinite sets counting is very simple. You point and count 1, 2, 3. But for infinite sets, standard counting completely failed. Enter the legendary mathematician George Cantor. He revolutionized mathematics by introducing cardinality, which represents the size or power of the extension of a set. So to compare infinite sets, Cantor didn't rely on counting. He used bijective mapping. Think of a bijection as a perfect one-to-one or onto pairing. If every single element of set can be paired uniquely with exactly one element of set, so with absolutely nothing left over, then their cardinality are equal. So mathematically, we write this as the size of A is equal to the size of B. So you have to remember the symbol is not means that determinant. So this brings us to our benchmark standard for measuring infinity in nature's numbers, denoted by the symbol n. So these are our standard counting numbers: 1, 2, 3, 4, and so on, extending forever. So we define an infinite set as countable infinite if it can establish a perfect bijection with these natural numbers. So Cantor gave the cardinality of this foundational baseline a special name, a leaf noun, so written as the size of the natural number equal to a leaf noun. So his key takeaway here is very simple. If you can arrange the element of a set into an order sequence, so which is a list of where there is a distinct first, second, and third item, even if it takes you literally forever to write it down, then the set is countable. So now that we have our rules, I'll pass the floor to Farid, so who will take us into a very strange hotel where these rules come alive.
Alright, thank you, Speaker 1, Mark Swanchi. Now let's look at the rigorous thought experiment designed by David Hilbert to show just how counterintuitive infinite set can be. Imagine a hotel with a countable infinite number of rooms which is room 1, room 2, room 3, and so forth. Usually, every single room is currently occupied. Suddenly, a new guest walks up to the desk looking for a room. In a normal finite hotel, the manager would turn them away. Sure, sure. But in a Hilbert's Crown Hotel, the manager has a clever trick. He simply shifts every current occupant up by one room. The guests in room 1 move to room 2, room 4, and move to room 3, and generally guests in room N move to the room N plus 1. This leaves room 1 completely empty for the newcomer. This proves a fascinating transferring truth, which is adding a single element does not change our baseline cardinality, which is k null plus 1 equal to k. But what happens when things scale up? Let's look at the scenario 2. An infinite bus pulls up, carrying a quantumly infinite number of new guests. Can the manager accommodate them all? Yes, by changing the route map. The manager broadcasts an announcement asking every current occupant to multiply their number room by 2. The guests in room 1 moves to room 2 moves to room 4, and room n moves to room n multiplied of n. What does this do? It moves all current guests into even number room. Instantly, An infinite number of odd number rooms, which is 1, 3, 5, 7, and so on, are cleared out. The infinite new arrivals from the bus are then smoothly directed into these empty odd rooms using the formula gk equals to 2k minus 1. Now for the ultimate challenge, scenario 3. What if a countably infinite number of buses arrive and each of those buses contain a countably infinite number of passengers? Alright, so to solve this, the manager turns to the mathematical uniqueness of prime numbers. The manager moves all current hotel guests to power of the first prime, which is 2, meaning a guest in the room n goes to the room and the power of n. Then passenger from the bus one are assigned the powers of the next prime, which is 3. So seat j goes to the room 3 to the power of j. Bus 2 goes to the power of 5 and so on. So because of the fundamental theorem of arithmetic, which states that every integer has a completely unique prime factorization, no two guests will be assigned to the same room. This thought experiment formally demonstrates a foundation rule of security. The union of countably infinite many countable sets is just countable, or as we write it as a k0 times k equals to k0. To show how we ground this thought experiment into formal mathematical proof, we pass the microphone to this speaker 3, which is Sylvester Giri. Alright, so before I pass the microphone to the Giri, let's continue for the introduction to this. Alright, so let's move from the hotel room to absolute mathematical region.
Intuitively, it seems like there must be half as many even integers as there are natural numbers. But using Cantor principle, we can prove otherwise. Let's define the set of positive even integers as e equal to 2, 4, 6, 8, and so on. We set up a function fn to e defined by fn equal to 2n. To prove this true bijection, we check two things. First, injection. If 2a equal to 2b, then dividing by 2 gives us a equal to b. It's 1 to 1. Second is surjection. Every single even number in our target set has a clear, unique per image back in the natural number. As you can see in the mapping table, 1 pairs with 2, 2 pairs with 4, and n pairs with 2n, because a perfect bijection is this. Both sets contain the exact same quantity of numbers. Even numbers are just as infinite as natural numbers. But what about rational number? Our everyday fraction. Fractions are incredibly dense. Between any two fractions on number line, there are infinitely more. Surely, there must be a larger infinity, right? Remarkably, no. Cantor solved this by aligning all positive fractions on an infinite coordinate grid where the row represents numerator and column represent denominator. He then applied his famous snake diagonalization path, tracing a winding line starting from 1 divided by 1, traveling diagonally across the grid. By following this continuous path and skipping, repeating duplicate like 2 divided by 2, 4 divided by 2, Cantor guaranteed that every single fraction will eventually get mapped to a sequential integer. This counterintuitive result, the rational numbers are strictly countable, sharing the exact cardinal same as the simple natural numbers. Up to this point, it might seem like every infinity is countable, but now we hit a threshold where infinity breaks its boundaries. Cantor proved that the interval of real number r between 0 and 1 is strictly uncountable using his famous diagonal argument. Imagine making a list of every single real decimal in the interval. Cantor showed that we can always construct a new decimal. Let's call it d by systematically modifying the diagonal digit on our list. We make digit 1 of d different from the first numbers First digit, digit 2 different from the second numbers, second digit, and so on. As shown on the slide, if our list contains values like 0.1395 and 0.2487, our contrasted value 0.2560 is guaranteed to be completely missing from the list because it differs from every single entry by at least one digit. Therefore, a bijection is impossible, proving that the real numbers represent a fundamentally larger infinity. So, why does all this abstract logic matter to us today? Because it forms the absolute bedrock of modern computer science. Every piece of computer code can be compressed into a finite binary string of ones and zeros. This means the total set of all possible executable programs is countably infinite. However, the set of all possible mathematical decision problems we might want to solve is uncountably infinite. The consequences are profound because the problem vastly outnumber programs. There are infinitely many more problems that computer can never solve, such as Alan Turing's famous halting problems. Infinity isn't just a philosophical concept, it sets the hard limit on what our technology can achieve. Thank you very much for your time.
So, Ross, thank you for joining us on this exploration of the infinite. So, we hope this video has provided clarity on the beauty and complexity of sector. Thank you.